with this guy, it would give us again always the alpha, the first element. It gives us always the first element. So this indicates, this vector here is an indicator. We can use it as an indicator that gives us the parameter that we are interested to be tested. So and now the question is, so why are we doing this exercise? So we want to construct this guy here. So we want to come up with a method that constructs us our capital R. Of course we can define the matrix, but as soon as the dimensions become more like larger, or our model becomes more involved, then obviously we need to have a method that makes it simple. Yeah. Let's take this away. We have defined our R. We know what our R looks like. So if we take now the identity matrix 1, which has the dimension n by n, yeah, and in our case n is 2, but if we have a higher dimension, this matrix is n by n, and now we have the Kronecker product. We take the Kronecker product and use this R here. Yeah. What do we get? So what we get is a big matrix, yeah, where we multiply each element, what is here on the left hand side, yeah, which is our identity matrix, with this vector here. So which means we have here 1 times this vector, we have here 0 times this vector, we have here 0 times this vector, and we have here as last element 1 times this vector. That's how the Kronecker product is defined. So 1 times this vector, then we have here 0 times this vector, we have here 0 times our vector R, and here we have 1 times our vector R. Now let's take this away here below. And this is, if you multiply it out, what's that? 1 times this guy is 1, 0. 0 times this guy, this becomes 0, is 0, 0. Here next we have 0 times 1. 0 is 0, 0, 0, 0, and 1 times 1, 0 is 1, 0. And this is our R, right? So that's how we calculate our, or how we determine, how we code our R. Yeah? So we take the identity matrix times n by n, Kronecker, the indicating vector that gives us the corresponding element in each equation. Yeah. So our R is defined as identity matrix of dimension n, and it's symmetric, so we don't have to write n by n. It's clear if we have the identity matrix that is symmetric. Identity matrix of the dimension n, Kronecker product, small r, yeah, which is this guy here. This is our R. And we know if we multiply R times beta hat, yeah, what comes out is our it gives us our alpha hat 1 and our alpha hat 2. So which are the guys that we are interested in testing. Yeah. So this guy here, R times beta hat, gives us the corresponding elements in each equation. They are plugged into stacked into one vector that we are interested in testing, and that's of course an n by 1 vector. Yeah. So now we know what is R, we know what is beta hat, we know what is Q, we know what is sigma hat. Yeah. So next, we also need to know what is this guy here, yeah? This X with this Q above. Let's take this away. So now the question arises, what is this guy that we have here and here? So this guy here is defined as a block matrix where we have our regressors X on the main diagonal, and here we have a matrix that consists of zeros. Yeah. Our X matrix, we have already defined it earlier, you remember. X is defined as ones in the first column. It's a t by 1 vector of ones in the first column, and in the second column we have the observations of our regressor, and we have just one regressor, so we have just one vector here, which is the excess market factor in our asset pricing context. So the first observation, second observation, and here finally the capital T's observation of our X. Yeah? So that's a t by 1, t by 2 matrix. Yeah? And the 0 matrix here has the same dimension. It needs to have the same dimension as our X matrix. So our 0 matrix here, that is here below and above the main block, let's say, has consequently zeros. It's a t by 1 vector of zeros in the first column and a t by 1 vector of zeros in the second column. So the dimension is also t by 2. Yeah. So, and how do we construct now this guy? So again, we can use this trick. Let's define the identity matrix. Again, it's a 2 by 2 matrix, or in general it's n by n, yeah? Depending on how many equations we are dealing with. Yeah? If we are dealing with 30 equations, that's a 30 by 30 matrix. Yeah? But in our case, n is 2, so we use this identity matrix here. Kronecker product again times x. And our x matrix we have here defined already. It's the same for all of these equations. So we have ones in the first column, and in the second column we have the time series observation of our x variable, yeah? x1, x2, x3 until x capital T. Yeah? And that's very simple what comes out, obviously. So once we have coded it correctly, things become very simple. So what happens here, yeah, so again, the Kronecker product means multiply each element in the matrix on the left hand side with the whole matrix on the right hand side. So again, we have to multiply, we have here 1 by x 0 times x, 0 times and 1 times x. Yeah. So again, so we have here our x matrix consisting of ones and x1, x2, x capital T. Here the same thing. Here the same thing. And here the same thing. Yeah. Here and every matrix is the same like here. So it's our x matrix. Yeah, here. So what comes out then, if we multiply 0, if we multiply every element here with 0, what comes out is this guy here. Yeah? A T by 2 matrix of zeros. And if we multiply this matrix here with n, and it remains the same. Yeah? So we get exactly our matrix that we need, yeah? This xq matrix that we have here and here. Hence, we can we calculate xq as identity matrix, dimension n, Kronecker product, our x matrix. And of course, now we can play around. So if we have more regressors here, then of course our x matrix becomes bigger, yeah? But it doesn't change this rule here. Yeah? So this remains the same. If we have two equations, n is 2, yeah? And we have here, let's say, 5 more regressors, yeah? Then obviously this matrix here, we multiply this matrix here with the bigger matrix. Huh? And what comes out then here is a bigger matrix. But everything else remains the same. So now we have defined what we have here, our xq as well. And now basically we have all the ingredients here, yeah, that we need for our equation. And now we could estimate our test statistic lambda. Yeah? Now let's take this away. Probably in the term paper that we are supposed to write, you will probably have much more than 2 test assets. Yeah, just as you know. So now we have defined all the ingredients here. Now, and it's basically like cooking. And now we put everything together, and we get our estimated test statistic lambda. And now remember, so we will not talk about this. So now remember that this r times beta hat minus q transposed is alpha 1 and alpha 2, right? So here, this is this guy here, alpha 1, alpha 2 is here. This is this guy here, what is here on the left hand side. And this is multiplied with what is here on the right side. And this guy here, it's inverted, so it's below the equation. So what is in our lambda hat, yeah? So what is in the numerator of the equation is obviously something like this. It's alpha 1 and alpha 2 times the same, not transposed, as a column vector, alpha 1, alpha 2, and then here below in the denominator obviously we have this guy here, this expression here, which is here. So again, so what is this? Now we have to remember the calculus rules for vector calculus. So it's obviously the scalar product. It is 1 by t times t by 1, 1 by 2 times 2 by 1. How do we build a scalar product? So we multiply this guy with this guy, which is alpha 1 squared plus second guy times second guy plus alpha 2 squared. Yeah? And again we have here downwards this huge expression. Yeah. So what is intuitively speaking here going on? So we remember from statistics that that a squared or the sum of squared normally distributed random variables is chi-squared distributed. So we have the alpha, given our assumptions. The point estimators are normally distributed, law of large numbers, and so on and so forth. So and our point estimators are squared, normally distributed and squared. We have two squared normally distributed random variables. That's why our test statistic is chi-square distributed with 2 degrees of freedom. If we have 30 test assets, we have here 30 guys going on, and that are squared, 30 random variables that are normally distributed and squared. The sum of 30 normally distributed random variables that are squared is chi-square distributed with 30 degrees of freedom. And what's going on here in the denominator? So we have to think about it. All this is defined for standard normally distributed random variables, with 0 mean and standard deviation of 1. Our alphas here, obviously, they are not standardized. So what's going? You can think about it. You can think about of what is in the denominator.